Hey, and welcome back to AIT 2101. This is the third installment of our vibration analysis lectures. We've talked about what vibration was, the four forces of vibration, and we talked a little bit about some of the impacts of vibration. We talked about some additional forces that are asserted onto our equipment as a result of simply imbalance. And the imbalance is just one of the vibration forces that a machine can experience. And it's usually the root cause of some of the other failures, such as bearings. And so we'll kind of continue to dig along with that. So anyway, going into our third part on vibration analysis. Okay, and again, I showed you some pictures of some bearings that kind of got trashed as a result of some of the imbalances and problems that that caused. Okay, so we're going to touch a little bit on bearings, but we're not going to dig real deep into bearings. So I just want to go into a little bit about bearings. For most of you, I think most of you know what a ball bearing is. This is a very small one. It's not anything nearly like you'll see the size of an industrial piece of equipment. But what you've got here, kind of the anatomy here, is you've got this inner race right here that the shaft passes through, okay? And we're wanting that shaft, and my finger representing the shaft, we're wanting it to be able to turn and transmit rotational or radial forces throughout that machine. And it does that, and we on the inside part of this inner race is a groove in which these various, looks like about 6 or 7 balls ride in, and they are riding on the outer race as well. So they're kind of sandwiched between the inner and outer race, and there's very little play between the two, and they rotate like that. Okay, so that's a typical roll of ball bearing. Okay. And the bearings are rated based on the intended load in which they're expected to carry. Okay, if you remember our fan blower graphic that I had up here with the 2 pillow block bearings in the shaft and the fan impeller, and also that sheave that helps is used for the belts to drive that. That's the intended load that the bearings are supposed to support or supposed to carry. And obviously, you don't want to make it right up to the maximum amount that the bearing can carry. You want to build some a safety cushion in there when you're designing a machine. When the machine designers do this, they want to make sure that they can cover some additional loads that are just as far as beyond the static load. Okay, they also want to build in enough beef or enough meat in there to handle the dynamic loads that we're going to talk about a little bit later too. And again, these loads, these are all machine forces. These are radial, the axial loads. These are all exerted on the bearings. Okay. Now, the life of a bearing decreases the second it goes into service. Okay, that is a true statement about 99% of the time. Okay, and I'll challenge this statement because from personal experience. Okay. So, at one of the plants I worked at, it was a Friday afternoon, and I had my vibration data collector, and I was running around collecting all the information on this particular fan assembly. Okay, and this fan assembly was one of 5. Okay, and it was mounted with pillow block bearings like you saw earlier. And we changed the bearing out. Got mechanics up there. It was a Friday afternoon. It was late, hot. It's time to go home. And I said, "Tell you what, we're going to leave this machine shut down." They were already finished, and I needed to take some baseline data, but I thought, I'm going to wait and take it Monday morning. So we left the machine locked out, and again, it was one of 5, and the other 4 blowers were running over the weekend. And so went home and came back Monday morning and said, I've got to take that baseline reading and get a good reading on what a good bearing looks like on this machine, and we can start trending it through failure. Okay, so I put my equipment on there, and I started pulling the data off of it, and immediately it showed it was a bad bearing. I was like, how can that be? Did we change the wrong bearing? What happened? Because, it's a brand new bearing, and it was showing defective right out of the gate. Now, it's kind of hard to believe, but data is what it is. I even checked some of the other blowers, and they were running right. So I went back, and bottom line is I had to get those mechanics up there and have them change that bearing on Monday morning. They were ready to string me up, and rightfully so. But here's what saved me. So we got it changed, put the new bearing on. We fired it up immediately. Vibration levels way down like they should be. Okay, like I was expecting to see them that Monday morning. And as it turned out, we took it, took it to the shop, figured out what's going on with this bearing. Well, we cut it open, and you can't see this in the camera, I'm sure, but there are little etch marks on this outer race of this pillow block bearing. And that shaft sat in there over the weekend. Remember, you have 4 other other fan units, and they are vibrating, and that vibration is transmitting through the floor up through this idle machine, this sitting idle. And the vibration was causing the shaft to move, to jump up and down inside this bearing. And the rolling elements were sitting there hammering little divots into the outer race, so that when we fired it up, those balls fell into those divots and was creating a vibration signal, and it was so severe that it looked like the bearing was defective. It was indeed defective, but it had no life on it whatsoever. It had 0 runtime on it. So that is my one experience where I can dispute this statement that the life bearing decreases the second it goes into service, the second you turn that machine on. Actually, it can go into failure before then. A lot of motor manufacturers will recommend that that if you have a warehouse that has several spare motors in there, that you turn those shafts of the motor 90 degrees every month or 2 months or something like that, and it keeps them from pounding notches in the same place as they would do if the shaft was not rotated. So they have you rotate. Also kind of keeps the grease fluid as well. But anyway, moving forward, this is the bearing. I showed you here, this graphic here. This is the outer race, the inner race, and the balls that go in there. Okay, and each one of these vibrates at a different frequency. Now, later lectures we're going to dive a little deeper into this, but the bearing can give you different frequencies. One bearing can give you multiple frequencies coming out of there. The frequency of the inner race and the outer race of the ball, they're all different. Okay, so they're all. So when we say we have a bad bearing, a lot of times with that particular bearing, I was able to dial in and show that the outer race was damaged. I didn't know why it was damaged until we cut it up and found out. But I was able to say the outer race is bad. And we cut it up, and sure enough, it saved my skin because, like I said, those mechanics were ready to string me up. But it turned out to be true. So anyway, just let you know that several vibration frequencies could be at play within bearing. Okay, and so when we talk about bearing life, we talked about it, kind of heading toward its end of its life the second we fire that machine back up. You can actually calculate and predict how long a bearing will last. Okay. There's that formula for it too. When we have L sub 10, okay, that's the number of hours that a bearing is expected to last. Now, in this formula, we have 16,666 is our fixed number. That is our constant, okay? And we divide that number by the RPM of the shaft that the bearing is turning at, or the shaft that's in the bearing, okay? So we divide that number, then we take that, and we take the rate, the rating of the bearing, the load rating of that particular bearing, and every different style and model has its own load rating, what it's expected to be able to carry and perform and live its full life. Okay, so we've got that rating, and we divide it by the amount of load we are actually putting on the bearing itself, okay? And then we're going to cube that and multiply these two. So let's kind of roll through this just a little bit, okay? So again, the rate is the capacity of the bearing that is designed to carry. The load is what we're actually putting on it. And of course, the RPM is the shaft speed, and 16,666 is a fixed number. Okay, so let's plug this in. Okay, and here's our look again. Now remember, the load that we're going to put on here. For example, when we talk about putting a load, we have the weight of the shaft, the weight of the impeller, and the weight of the ship. We also have to consider the amount of force or tension that the belt is putting on this, because as you're pulling that belt tighter, it's going to pull on that shim and shaft assembly, and it's causing additional forces on the bearing. So you can't ignore those. Those have to be included as well. So let's plug in some numbers real quick. Okay, so we're running at 1,800 RPMs. We're going to use this number a lot because it's a standard RPM of a three-phase AC motor used in so much of manufacturing. And then the bearing I have selected is an SKF MRC 301. You don't need to memorize any of that, but it does have a load rating of 2,190 pounds, okay, of force, all right? So we divide that by the actual force, and I just made this number up here for our mathematical purposes. Let's say that fan assembly and the shiv and the blade and everything weighed 150 pounds, okay? So we're going to divide these, cube it, divide these, and multiply the two together. And again, we're using a 301 right there. And what happens is we can have a life expectancy based on these conditions, this bearing and this load, of 28,787 hours, which equates to about 3 years and 3 months of 24/7 running, never shutting off. So we can expect that bearing to last for about 3 years and 3.25 years, okay? So let's talk about, though, remember from the previous lecture, we talked about the impact of 4 ounces on our impeller blade when it's mounted or when it's being exerted 12 inches from the center line of the shaft, all right? And we said that we created a 275-pound additional weight, okay, additional load. So if we add that force on top of the load that the machine sets as it's designed, okay, this is what we're going to happen. This is what's going to happen here. We're going to still use the same bearing, still using 4 ounces, but now we're going to take that imbalance that we had and the force that, and instead of 150, remember we said 275, so we came up with 425 pounds being of our load right there on our bearing, being exerted onto our bearing. So when we do that, when we run the numbers just like we did before, we wind up with a life expectancy of about 1,265 hours. That's not quite 2 months. So as a result of that imbalance, we have really cut the life expectancy of that bearing, or those bearings I should say, down from about 3.25 years to less than 2 months. Okay? So what this means is that we're not going to have a very reliable machine very long. We're going to be changing these bearings roughly every 2 months, okay? A little bit less than that. Well, the problem with that is that we continue to change them, and we change them, and we change them. We're not fixing the problem, okay? So what we got to do is we got to figure out why, what vibration is really going on here, and there's going to be a lecture there talking about the different vibration signatures. But what we got going on here is we have an imbalance that we need to address, because if we don't, it's going to continue to have our bearings fail. And a lot of people won't do that root cause failure. They won't look deeper. They'll say, oh, we got a bad bearing. And every 2 months, we got a bad bearing, bad bearing, bad bearing. They're not drilling down, and they're not getting to the root cause. The root cause is the imbalance. And it's causing this to happen on our shaft, which is then transmitted to our bearings. Okay? And so really we don't have a bearing problem, we got an imbalance problem, we need to take care of that. But you can see now how that additional 4 ounces, 12 inches from our center line of our shaft is having a big impact on how often we're going to be changing these bearings. Okay? Now, as far as our calculation goes, we've got some other forces at play. Okay? Environmentally, is the bearing in excessive heat? Is it in a clean environment? Is it, there's a lot of contamination floating in the air or near the ground or something like that? And is that coming into play? Okay? And also lubrication practices. Are we greasing the bearings enough? Are we over greasing? Studies have shown that the #1 cause for bearing failure is actually over lubrication. Okay? You can't over lubricate to where you create too much heat, and the wax and the soap in the grease starts to become very liquid, and with the liquid out goes the lubrication properties, and you lose a bearing, and it looks a lot like you've lost a bearing due to lack of lubrication, when in fact it's been over lubricated. Okay? And again, the correct application. Sometimes machine builders, in order to cut costs, they will design the machine to run with the bearings right up to their maximum potential or their maximum capability without any excess buffer built in there. So correct application has a lot to do with that formula as well. So anyway, vibration cannot be ignored. I promise you, if you ignore the vibration, it will come back and bite you. Okay? If you ignore that vibration in your front, in the wheel of your car, in the tire of your car, I guarantee you, your front end's going to wear out a whole lot faster. You've got ball joints, you've got tie rods, or excuse me, rod ends, and then other steering components, other suspension components are going to suffer as well. So, and particularly with our manufacturing, downtime is money. Okay, we're going to talk a little more about this too. But if you plan and schedule maintenance is so much more economical as opposed to a breakdown maintenance. All right, you're going to have to sometimes either hot shot or on the ground or fly parts in. You're going to have overtime. A lot of times overtime, studies have shown that most of your industrial accidents happen when people are working overtime. And you've got a machine that's sitting there that you're paying for, and it's not making you any money. And also, customers are expecting you to have a product for them, and you left them high and dry. So you're losing some credibility with your customers as well. Bottom line though is that downtime is money, and you need to address that quickly. All right. And vibration analysis is one of the tools that we can do that with. So that's going to wrap up this chunk of the lecture series. So if you will, just again be taking notes because you will need them for quizzes. You're also going to need them for our in-person mandatory lab. So make sure you're taking those. Got any questions, come and see me. Other than that, be sure to queue up the next video. Thanks for watching.